We ended our last fluids video by talking about applications of Bernoulli's principle. What we're going to talk about in today's video is Bernoulli's equation. Bernoulli's equation actually comes from the law of conservation of energy, which we learned about last year. So in case you don't remember, let's talk a little bit about conservation of energy. Remember that within an isolated system, the total energy of the system is constant. It just gets changed from one form to another. Kinetic energy to gravitational potential energy to thermal energy to spring potential energy, chemical energy, all different forms, but the total energy when we add them all up is equal to a constant. And remember, we talked about if we wanted to change the amount of energy in a system, well then we needed to do work on the system. What we're going to talk about specifically today is that work, which is done on the system, our fluid, will result in a change in the kinetic energy and possibly the gravitational potential energy of the fluid. So let's first start by talking about work. The change in pressure in a fluid as it goes from a larger area to a smaller area does work, right? When the fluid moves from a large area to a small area, it speeds up. All right, which means there's that force, that pressure differential that creates this force. And remember that work doesn't just create a change in energy, but work comes from a force that's applied across a distance. And of course for fluids, force is pressure times area. So our work, which is force times the change in distance, we can also write for fluids pressure times area times that change in distance. Remember, area times a change in distance, well, that's just a volume. So when I have this situation where I have differences in pressure, then the work is equal to the pressure difference, P1, the pressure in area 1 minus the pressure in area 2, times the volume. Now, in the case of our horizontal pipe here, work is being done to change the kinetic energy of the fluid, right? It's speeding up or it's slowing down, but we're changing the velocity or the speed. And remember that kinetic energy is the energy of motion, kinetic energy being 1/2 mass times velocity squared. But for fluids, right, we don't think of mass per se. We think of it more in terms of density and volume. So if we rewrite our kinetic energy equation, we get 1/2 density of the fluid times the volume times the change in velocity squared, right? This is just the mass. So in this case, the work is changing the kinetic energy in our horizontal pipe. So if work equals a change in kinetic energy, then we have the pressure difference times the volume is equal to the difference in the final kinetic energy, 1/2 density volume times the velocity at point 2 squared, minus the initial kinetic energy, or the kinetic energy at point 1, 1/2 density times volume times velocity at 1 squared. Of course, that's for a horizontal pipe. But a lot of pipes in our house actually change height. So if height changes, right, we've got another energy that's changing, and that's gravitational potential energy. Remember when we talked about gravitational potential energy last year, gravitational potential energy, right, is mgh, or mass times the acceleration due to gravity times the change in height. So for our fluid, again, getting rid of mass and inserting density and volume for mass, we get density of the fluid times the volume times the acceleration due to gravity times that difference in height of the pipe, or the height at point 2 minus the height at point 1 with regard to some reference point. Now we can put it all together and we get this really ugly looking equation which has our work component. Here's our work, the difference in pressure times the volume is equal to that change in kinetic energy plus the change in gravitational potential energy. Yeah, it's pretty scary looking, isn't it? Well, now we're going to simplify it, right? We can do that by getting rid of these volumes. And we can rearrange it so that we put all of the stuff for one point on one side of the equation and all of the stuff for the other point on the other side of the equation, and we come to Bernoulli's equation for an ideal fluid. Pretty scary looking, huh? So we have the pressure, the kinetic, so the work part, the kinetic energy part, the gravitational potential energy, all for part 2 on one side, and that's equal to the same exact stuff, but for point 1 on the other side of the equation. Now again, this is for an ideal fluid. That would be frictionless, moving in a streamlined flow, incompressible. So if we looked at real fluids, we would have to add some more stuff to this. Maybe have to do some integrals. Let's take a look at how we would use this lovely equation. I have a pipe here which has water moving through it, so the density of water is 1,000 kilogram per meter cubed. And it's flowing through a pipe at point 1. I have a gauge pressure of 75 kilopascals, and the water is moving at a speed of 5 meters per second. The diameter of the pipe at this point is 6 centimeters, and then the pipe narrows and raises up 2 meters. The new diameter is 4 centimeters, and what I want to know is what is the gauge pressure in the upper part of the pipe? Well, the first thing we need to do is write down Bernoulli's equation. And then let's rearrange it to solve for pressure 2. Go ahead and do that. So this is what you should have right now, our rearranged equation. Pressure 2 is equal to pressure 1 plus the difference in the kinetic energy plus the difference in the gravitational potential energy. Of course, we can simplify this a little bit to cut down on all our calculations by pulling out the density part of each of these terms. So I know what pressure 1 is, or do I? I know the density of the fluid, I know the velocity of the fluid, and I know the height difference, but I am missing something. What am I missing? Velocity 2. Well, how am I going to figure that out? I can't solve this if I got 2 unknowns. The equation of continuity that we learned in the last video. All right, the velocity at point 1 times the area of point 1 is equal to the velocity at point 2 times the area at point 2. Well, I know the velocity at point 1, and I know the diameter at point 1 and point 2. I can do this. All right, go ahead, plug your numbers in, and find the velocity at point 2. If you did that, and you do your math correctly, don't forget you got to square those diameters, you should get 11.25 meters per second. Well, now we have the velocity at 2, but what do we do for the pressure at 1? We're given the gauge pressure, right, 75 kilopascals, but in Bernoulli's equation, that's the absolute pressure. So if you remember from our very first video on fluids, absolute pressure is gauge pressure plus atmospheric pressure. So to our gauge pressure of 75 kilopascals, I need to add atmospheric pressure, or 101.3 kilopascals. And of course, let's put it into pascals, the SI unit. So 176,300 pascals. All right, now you have all your numbers, so go ahead, plug them in, and solve. So pause it, do that, and then let's see if you got it right. If you solved it correctly, you should have an absolute pressure at P2 of 105,900 pascals. Now, this is the absolute pressure, but I'm pretty sure the question asks for what is the pressure on the gauge read. So that means I need to subtract out that 101.3 kilopascals. So don't try to subtract 1 atmosphere. And you should get 4.6 kilopascals. The question is now, does that make sense? Does it make sense that the pressure at point 2 is less? Well, first of all, let's look at the diameter, right? We said when the diameter goes down, the fluid moves faster, and if the fluid moves faster, then the pressure is actually lower. Well, that would correspond with that, right? The gauge pressure at point 1 is 75 kilopascals, and at point 2 is 4.6. But also, we gained elevation. And hopefully that also makes sense that that would reduce the pressure. Now, there's one more thing I want to talk about with regard to Bernoulli, and that's a special case called Torricelli's theorem. This is actually come up with by Evangelista Torricelli, who was an Italian physicist and mathematician. In fact, he was the guy who invented the barometer. He actually filled a tube with mercury, put his hand over it, and inverted it in a plate. Maybe that's why he just made it past his 39th birthday. I don't know. Anyways, so what Torricelli found was that if there are equal pressures on something, say like a tank of fluid, right? If pressure here, right, is atmospheric pressure and the pressure here is atmospheric pressure, then that term cancels out of the Bernoulli equation. And if the area of this exit hole is small compared to this area up here, then we can also say that the velocity up here is very small compared to the velocity here. And that will cancel out this term as well, leaving us only with a difference in gravitational potential energy for our fluid and our little kinetic energy component from the exit hole. And if we rearrange and solve this, right, we can cancel density out of this equation. We end up with a very simple equation, which is this. Velocity is equal to the square root of 2gh. Now, this is only a special case. You can't do this with every Bernoulli type of problem, only when I have like an open tank or a dam. Right, that's a dam, a wall with water and a little opening or a hole or a leak. We can use Torricelli's theorem. So let's actually do that. Let's take a look at a Torricelli problem. So I have this dam here and it sprung a leak, which is 20 meters below the surface. What is the emergent velocity? Well, 2 times the acceleration due to gravity, 9.8, times 20. And then don't forget to take the square root. Oh, that's not too bad. Too bad we can't do that with every Bernoulli equation. All right, that's it for fluids. See you in class.